Welcome back, Nature and Code. We're in Chapter 6, Natural Selection, and we just looked at the second type of natural selection, which is balancing selection that you see here. Balancing selection is very interesting because it means that independent of where you start here with your p-value, as long as it's not 0 or 1, of course, then p will converge to a stable equilibrium somewhere between 0 and 1, which means that genetic diversity will be maintained, will be balanced, so the alleles will be balanced in this population. And that's really quite interesting. Now, let's go back to our slides and let's take a look at the third type of selection that we can look at here with this code. So, we just looked at directional selection and balancing selection. Now the final type here is disruptive selection. Disruptive selection occurs when the heterozygous effect H is larger than 1, which means that the fitness of the heterozygote is lower than the fitness of both A2, and of course also of A1. So it's the lowest, it has the lowest fitness of all the genotypes, giving rise to this type of fitness valley. So what are the consequences of that? Well, let's first take a look here at delta P versus P. So let's go ahead, change the code so that we can see what's happening here. And the code change, of course, is quite simple. So open the file delta P versus P if you haven't done this already. And now you simply need to change this value here. So we had a negative value here for balancing selection. Disruptive selection requires that this value is larger than 1. So let's just set it to 1.5, say. Okay, save this, and now go over to the browser, reload, and here's what we get. Oh, this is interesting. This almost looks mirrored, doesn't it? So now over here, when p is small, we get negative delta p values. And when p is large, we get positive delta p values. So what does that mean? Well, let's see. Let's again start here somewhere at low values of p. And then, this is interesting. Well, because delta p is negative, you'll move a bit to the left. And as long as delta p is negative, you keep moving to the left. So basically you're pushed away all the way to 0. Okay, what happens when you're over here? Well, when you're over here, delta p is positive, so you're moving a little bit to the right, and you keep moving to the right here because delta p is positive, so you will always move up to 1. So, okay, that is interesting. It means that when you start here, you will move to 1, and the allele will go to fixation. When you start over here, you will move to 0. And there seems to be this equilibrium here where delta p is 0 and nothing changes. So that's interesting. Let's take a look if that is true. So we want to now modify this p versus time code to generate the dynamics of disruptive selection. So let's go to our code and let's open the other file. Open p versus time. Okay, I'm going to close this tab, the file window here, or the file tab. Okay, so let's set this back. Let's set this s back to 0.1, just to be consistent with what we had before. And let's set h to 1.5. Right? We want an h value that is larger than 1, and in the previous delta p versus p example we used 1.5 as well, so let's go ahead and do that. Okay, save it, and now reload this, and here's what you see, and this is now very intriguing, isn't it? If you start at low values, indeed you will go to an equilibrium at 0, so the A1 allele will get lost. If you start at a higher value, you will go to 1, which means that the A1 allele will get fixed. So that's exactly as we predicted. And here's this interesting line, right, at, it seems, 0.25, where you're at this equilibrium where delta P is 0, so you're not moving away. However, the slight difference here is that this is actually not a stable equilibrium, right? Even if you are at this equilibrium and you're pushed away just a tiny little bit, instantly you will, if you push to the left, you will instantly start converging to 0, and if you're pushed a little to the right, you will instantly start converging to 1. So this is kind of an artificial, or rather unstable, equilibrium. And we can demonstrate this quite easily in our code. How can we do this? Well, it's actually quite simple. All we need to do is we need to add, to the P, we need to add a little bit of noise here. So at the moment, you can see that this value seems to be at 0.25 here. And that is where indeed delta P is 0. It seems to be at 0.25. So why don't we go ahead and simply in our code here, when we initialize this value, when we sort of set up these initial values of P, why don't we add a little bit of random noise here, just a little bit. So I'm just going to add here math random. Now that of course would not be a little bit, that would be a value between 0 and 1. So I'm going to multiply this value here with 0.000001. It's just a small value. So now this product here will be very small, right? I'm going to put this in parentheses just to make this a little clearer. So this will be a very small number between 0 and 0.000001. So a very small number that I'm going to add here to this initial P. But still, if you save this and then go back to your P versus time and you reload this, you'll see the following. Isn't that fascinating? And of course, if you reload it, it'll move a little bit because this initial value has a tiny little bit of randomness to it, and that causes these effects here. But fundamentally, it is now not exactly at 0.25. It is just a tad bit removed from 0.25. So it takes ages, to start increasing fast. And why is that? Well, it's because you're not at 0.25. You're just a little bit here to the right. I mean, you can hardly, you won't be able to see this on this graph, but your delta P's will just be very, very small too. And so you really sort of make very, very small baby steps moving away from P equals 0.25 until you finally get into a parameter space here where delta P starts picking up considerably, and that's when you start seeing this uptick here. But in any case, the major point is that this equilibrium here is an artifact. It's not stable, and that brings us to the final conclusion of this video, which is that disruptive selection, one of the alleles will go to fixation, and you cannot necessarily say which one it is, because it will depend on the initial value. It will depend where you start. That's quite interesting too, don't you think? Because we always think of evolution as this sort of clear-cut process, a deterministic process, especially in the deterministic world here where we don't have stochastic drift. But it's not true. It depends on the initial conditions. And once again, it turns out you can actually calculate this value here at which basically things are going to be fundamentally different, right? This value here is quite crucial. If you're left of this value, the allele will get lost. If you're on the right-hand side of this value, the allele will go to fixation. So this is an important value. Well, what is the value? How do you calculate this value? Well, lo and behold, it turns out this is exactly the same value. It's exactly the same formula, h minus 1 divided by 2h minus 1. And let's once again make the example with the values that we used in the code. So I'm going to use the red color here now for disruptive selection. So we had 1.5, which means here we have 1.5 minus 1. which is of course 0.5. And here we have a 2 times h, so 2 times 1.5, which is 3, minus 2. And here you can see 0.5 divided by 2 is of course 0.25, and that's exactly what we saw. So 0.25. Okay, and that is sort of concludes this video. It also concludes the various types of selection of natural selection. So we have directional selection, we have balancing selection, and we have disruptive selection. And we've just seen the example here of disruptive selection and what happens in this case. So it's worthwhile reflecting once again what these types are. So directional selection means the allele will go to fixation. It doesn't matter where you start, it will just go only one direction, which is fixation. Balancing selection will also only go into one type of equilibrium, but it's not p equals 1. It is indeed p equals some value between 0 and 1. And this is really important because that means it can maintain genetic diversity. It can maintain both alleles in the population. And that's because the heterozygote has the highest fitness. And finally, disruptive selection. Disruptive selection will get rid of one of the alleles, but which one it is will depend on the initial conditions. And that concludes these different types of selections. In the next video, we're going to talk about another type of selection, and that is when many species interact with each other and affect each other's fitness, and then we'll get coevolution, and that's quite interesting. So see you in the next video.